Hi, I'm Colin. We're going to be talking about inverse functions in this module. Let's start off by looking at something called the doubling function. Let y be a function of x given by a very simple rule, f of x equals 2x. That is, the function simply doubles any input, or x value. So when the x value is, for instance, 3, the doubling function f would output the y value 6. In terms of terminology, we sometimes say that the function f maps 3 to 6. The inverse function of f sends the outputs of f back to their respective inputs. That is, the inverse function maps y values back to their original x values. So for our doubling function, throwing 6 into its inverse function will result in the 3 being recovered. Therefore, the inverse function of the doubling function must be what we call the halving function, since the inverse operation of doubling is halving. Despite the curious notation, keep in mind that f inverse is not the same as f of x to the power of -1, which is an entirely different concept. Because f inverse effectively sends y values back to their original x values, it essentially undoes or cancels the operation of the original function. For example, if you throw 3 into the doubling function, you'll get 6. But if you then throw this 6 into its inverse function, the halving function, you'll precisely recover the original input 3. This is because the operation of halving precisely undoes or cancels the operation of doubling. Moreover, the order in which you apply the operations doesn't matter. Just as how halving cancels out doubling, doubling will of course also cancel out halving. So if you halve first, and then double, you'll still end up with the same number. So the doubling and the halving functions are actually inverse functions of each other, and we say that they are mutually inverse functions. They will undo each other in any order. Algebraically, this so-called cancellation property of inverses can be stated in the following way. For any input x in the domain of f, if you apply the function f, and then immediately undo the function by applying its inverse function on the output, you'll recover the original input. So the operations of f and f inverse cancelled each other out. And since f and f inverse undo each other in any order, we can apply f inverse first, and then f, which also recovers the original input. Note that the operation of letting the output of a function be the input for another is called composition, and the functions on the left-hand side are examples of what are called composite functions. A complication that arises with inverse functions is that they don't always exist. That is, for some random function f, an inverse function may or may not exist for this function, and it depends on the domain from which the function f draws its inputs. Let's explain in a bit more detail. Consider the simplest quadratic function, f of x equals x squared, whose graph is the simple concave up parabola with vertex at the origin. What's the natural domain of the function? That is, what's the set of all the possible inputs? Well, we can certainly square every single real number. Nothing can go wrong there. Thus, the domain is the set of all the real numbers R. Now, if we input 2 into f, the output will be 2 squared, which is 4. And if we square negative 2, we also get 4. Since both 2 and negative 2, all squared, both equal 4, the output y equals 4 can be traced back to two possible inputs, x equals 2 and x equals negative 2. Now recall that function outputs must be unique. So would the inverse function of f send 4 back to 2 or negative 2? This is quite ambiguous, and so we say that the function f of x equals x squared has no inverse function on its natural domain of R, the set of real numbers. But notice if the left half of the graph magically disappeared, as if we artificially restricted the domain of the function f to only the positive x values, then an inverse function could unambiguously send 4 back to 2. No problems. Or if the right half of the graph magically disappeared, as if we artificially restricted the domain of f to only the negative x values, then an inverse function could unambiguously send 4 back to 2 also. No problems. In summary, we've discovered that the function f of x equals x squared does not have an inverse function defined on its entire natural domain, all the real numbers. But if we can artificially restrict the domain to say only the left half or the right half, then f will be invertible on this restricted domain. In general, a function needs to be what's called injective, or one-to-one on a given domain, in order for an inverse function to exist. Roughly, one-to-one means that any output of f is the destination for only one input. That is, you can't have two different x values that goes to the same y value. Therefore, the function f of x equals x squared is not one-to-one, since we saw earlier that the y value 4 is shared by two different x values, plus 2 and minus 2. Now, if the function isn't one-to-one, then not all hope is lost. You'll just need to artificially restrict the domain of the function so that the function does become one-to-one on that restricted domain. You can then define an inverse function on that restricted domain. So the property of a function being one-to-one is very important. How can we easily tell when a function is one-to-one on a given domain? There are two tests commonly used, called the horizontal line test and the monotonic test. To employ either of these tests, you'll need to first sketch the graph of the function. Okay, let's first look at the horizontal line test. The test says that if you can place a horizontal line anywhere on the xy plane, and it only ever touches the graph of the function at most once, then the function passes the horizontal line test, and we can conclude that the function is one-to-one. Rather than drawing lots of horizontal lines, you may find it easier to grab your pen and lay it horizontally on the page, that is, parallel to the x-axis, and then run the pen up and down and observe how the pen cuts the graph of the function. If the pen only ever hits the graph once everywhere, then the function is one-to-one. Here, the function f of x equals x squared fails the test, because we can quite clearly see that any horizontal line above the x-axis will hit the parabola twice. But notice when we restrict the domains, the function does become one-to-one, since any horizontal line will now cut the graph at most once. Hooray! Another equivalent test is called the monotonic test. Roughly speaking, a function is called monotonic if, as we're traversing from left to right, the graph is either always going up or always going down. In other words, either always increasing or always decreasing. And the monotonic test says that if the function is either always going up or always going down, then it passes the test and we can conclude that it's one-to-one. Here, the function f of x equals x squared is decreasing at certain places and increasing at others. Specifically, the function is decreasing for all the negative x values and increasing for all the positive. Specifically, the function is decreasing for all the negative x values and increasing for all the positive x values. Thus, it fails the monotonic test, confirming once again that the function is not one-to-one. But notice when we restrict the domain, the function does become one-to-one, since the graph is now either always going up or always going down. For the purposes of demonstration, let's pick a restricted domain and stick with that choice for the rest of the module. We'll choose to restrict the natural domain of R to just the positive x values, including 0. An inverse function can now be defined on this restricted domain. Notice that the possible outputs are all the y values greater than or equal to 0. So here, it turns out coincidentally that the domain and range are the same set of numbers. That is, the interval between 0 and infinity. Okay, so we've established the conditions under which a general function f is invertible, and we've chosen a restricted domain for our example function f of x equals x squared upon which to define an inverse function. Once we're happy with all of this, how do we do things like find a formula for the inverse function, along with its domain and range? Oh, and what about sketching the inverse's graph? Let's focus on these questions for the remainder of the module. Let's start with finding the formula for f inverse. Since f inverse recovers the inputs of f, the first step is to grab the formula for f, which will currently have y or f of x as the subject, and rearrange it to make x the subject, since the inverse function is trying to get us back to the original x values. That means for our simple quadratic f of x equals x squared, let us first write it as y equals x squared. Now we rearrange the equation for x. To do this, we take the square root of both sides. This gives us x is equal to plus minus the square root of y. Notice the plus minus, which confirms that for every y value that the inverse function attempts to return to x, there will be two choices for x, which is problematic since the inverse has to be a function. But here, since we've restricted the domain to all the positive x values only, that means we're only squaring positive numbers, which means the inverse function must return these back to positive numbers. Thus here, we discard the negative sign and only need to consider the positive square root. Alright, having rearranged for x, the second and last step is to simply interchange x and y. Thus, the inverse function for the squaring function, where we're only squaring positive numbers, is therefore the positive square root function. In terms of the operations involved, squaring and square rooting, all of this should make sense, since we know that the inverse operation of squaring is square rooting. If you square a number and then immediately take its square root, you get back to where you started from. Note that if you had restricted the domain of f of x equals x squared to the negative x values, then the inverse function here would be the negative square root function. That's because if you take the square of a negative number, then its inverse function must return back this negative number. Okay, Now, given an invertible function f, let's talk about the domain and range of its inverse function. In a nutshell, it turns out that the domain and ranges of a pair of mutually inverse functions are precisely the same sets, just switched around. Let's try and make sense of this. Firstly, let's call the domain of f to be A, and its range B. So think of A as the set of inputs for the function f, and B as the set of outputs for f. Then the function f will map elements of the set A to elements of the set B. Now, since the aim of the inverse function is to take these outputs back to where they originated from, f inverse therefore takes its inputs from the range of the original function, and the outputs will land right back in the domain of the original function f. This means that the domain of f inverse is precisely the range of the original function f, and the range of f inverse is precisely the domain of the original function f. So in summary, the domain and ranges of two mutually inverse functions are just the same sets switched around. For our function f of x equals x squared, recall that we restricted the natural domain of all the real numbers to just the positive x values, including 0. So that the function becomes one-to-one on this restricted domain. And recall that the range is the set of all the y values greater than or equal to 0. In other words, the same set of numbers as the domain. Therefore, its inverse function, the positive square root function, has its domain to be precisely the range of the original function. And its range to be precisely the domain of the original function. Here's another important fact. The graphs of two mutually inverse functions are symmetric about the diagonal line y equals x. That means if you can sketch the graph of the original function, f of x equals x squared, taking into account its restricted domain, then all you have to do is reflect this curve about the diagonal line y equals x to obtain the graph of its inverse function. This can be a useful thing to know for graph sketching, since if you know how to sketch just one function from a pair of mutually inverse functions, you'll know how to sketch the other. By the way, if you're feeling game enough, you should have a good think about why this geometric property is true. As a hint, you know that the original function f would send the x value 2 to the y value 4, which could be graphed as the coordinate 2, 4. Its inverse function would send 4 back to 2, which could be graphed as the coordinate 4, 2. Observe that these 2 points are just reflections of each other about the diagonal line y equals x. Could you show this fact more generally? Anyway, that's it for now. We've motivated the basic notions of inverse functions, including what they mean and under what circumstances they're well defined, along with how to find their formulas, their domain and range, and how their graphs geometrically relate to those of the original functions. And we did all of this by focusing on some very simple pairs of mutually inverse functions, such as the square and square rooting functions. You should now go off and employ these concepts to harder examples. Some good ones to study include the sine and sine inverse functions, along with one of the most famous and useful examples, the exponential and natural logarithm functions, if you've covered that. Alright, catch you next time.